Sí, es que está ocupado esto. Bueno, buenos días a todos. Estamos aquí otro año más celebrando la Conferencia Santaló. Llevamos ya, esta es la edición número 17 de la Conferencia Santaló, que la organiza conjuntamente la Facultad de Matemáticas y la Revista Matemática Complutense. La Revista Matemática Complutense empezó hace ya 30 años, estamos de cumpleaños y celebraciones, y desde hace unos 9 años está en el índice del JCR, y en los últimos 2 años pues hemos tenido unas buenas evaluaciones, estamos en el primer cuartil y estamos celebrando todo el trabajo que tenemos y todos los buenos artículos que estamos recibiendo. Obviamente, detrás de todo esto hay un equipo editorial que ha venido trabajando, no el actual, sino desde hace 30 años, en hacer un proyecto importante, interesante, que ponga la Revista Matemática Complutense en el panorama internacional de la matemática, y además una facultad que apoya constantemente esta labor. Yo creo que cuando se dan estas dos sinergias, pues tenemos un buen producto, que es una Revista Matemática Complutense en un panorama internacional bastante bueno. Desde la revista seguimos teniendo la misma ilusión del principio para tener un producto de calidad y seguir organizando la Conferencia Santaló. Y bueno, me gustaría agradeceros a todos vosotros por participar en esta conferencia y por toda la labor que hacéis, sobre todo a los profesores y estudiantes de doctorado, en difusión y en mandar buenos artículos a la Revista Matemática Complutense. Bueno, simplemente termino agradeciendo al profesor Bernd Sturmfels del Instituto Max Planck de las Ciencias Matemáticas de Leipzig, y que es el conferenciante actual, y va a hacer la presentación José Fernando. Solamente me gustaría decir que una de las obligaciones que tiene el conferenciante Santaló es enviar un artículo a la Revista Matemática Complutense, y este es el primer año en donde el artículo ha salido publicado antes que se imparta la conferencia Santaló, y de hecho en este volumen de septiembre que ha salido de la Revista Matemática Complutense, que lo podéis leer online, está ahí además, ha salido ya publicado el artículo. El primer artículo de este número es el de Bernd Sturmfels con sus colaboradores. Bueno, voy a dar la palabra ahora a José Fernando, que es editor de la revista, porque va a hacer la presentación y va a ser un poco el que va a dirigir la conferencia.
I have to speak in English because he asked me to present in English in order that he could understand everything. So first of all, I would like to thank the lecturer Bernd Sturmfels. I also would like to thank Tomás Recio, who helped us to organize the first encounter with him. It is very difficult to present a huge mathematician as Bernd Sturmfels because he has a lot of publications, lot of citations, lot of prizes, lot of awards, lot of many things. He's in the editorial board of many journals he has been. So I am going to try, just a moment. Well, I am going to try to make a summary. I mean, I hope that he would like the summary because I have chosen what it was more impressive for me. Before beginning this conference, I spoke with him and I asked him how many students or PhD students did you have, and he said many. So in many things, like articles, I will say many, and then you will understand that there is a lot. For instance, I began looking for the number of publications, so I go to the usual database, which is called Mathestinet. So he has 260 publications, and then you go to citations, which is something that we usually look for, and he has 7,040 citations. Some years he has 400 citations. This means that this data maybe is expired today, so maybe we have to increase this. And he has been cited in Mathestinet, which are articles in mathematics, by around 4,000 authors. The Pca index of this professor, which means the Pca index is a number n of articles that at least has been cited n times. So he has in MathEstimate 40, which is very huge. 50 co-authors in mathematics, but if you go to other databases like Scopus, you find that he has 150 co-authors. But if you go to Google Scholar, who controls other types of manuscripts, other types of citation in archive, he has 24,500 citations. So you can imagine the kind of person we have invited this time. I mean, about positions, he has hold positions in Minnesota, Linz, New York, Berkeley, Kyoto, Leipzig, Berlin. At the moment, he is professor of mathematics in statistics and computer science in Berkeley, and also he is one of the 3 directors of the Max Planck Institute for Mathematics in Science. Subjects, he's a very transversal scientist, so he works in mathematics and computer science, but also in biochemistry, genetics, agriculture and biological science, engineering, economics. So you can imagine that he's a very, very transversal scientist. He has published in very, very important journals. For you students, the names I am going to say is doesn't important. I mean, you will not understand, maybe many of you, because you are not curious about which journals are important or not at this moment. But imagine that instead of speaking about articles, we are speaking about cars. So you will find names similar to Ferrari, Lamborghini, Lotus. So I'm going to say the names of the journals. My colleagues will understand. Annals of Mathematics, Journal of the American Mathematical Society, European Mathematical Society, Duke, Advances, Transactions, Mathematicianalen, Crele, Topology, American Journal of Mathematics. These are the ones in pure mathematics. I am of pure mathematics. I am not so sensible in the journals of applied mathematics. So other people, I mean, there are many things. He has also been the editor of many journals, these ones selected like Ferrari, Lamborghini, etc., which are also Annals of Mathematics, Duke, Foundation of Computational Mathematics, etc. He has also received many awards and prizes, like, for instance, the Alexander von Humboldt Research Prize in Berlin. He's also honorary doctor in the Goethe University of Frankfurt. He obtained a fellowship in Berlin, which has the name of Einstein. Maybe this name is familiar for you. And he also got this year the George David Beresford Prize in Applied Mathematics. So, I mean, the numbers, the names, and everything, are incredible. To finish my presentation, I just want to tell 3 small anecdotes. The first one is that in the 2013, I was in a congress. It was the first time I saw him. And it was in a congress of tropical geometry. I'm not expert in that thing, but I was curious about tropical geometry. And I understand almost nothing in every seminar. I was understanding almost nothing. But then he arrives, he gave a very nice conference for outsiders, and the people who was like me that were not insiders in the topic were able to understand many things. So I am sure that you today, he will make a big effort to try to explain you what he do. The second is that yesterday and all this week I prepared a little about the paper he has prepared. So I was saying, okay, I have his paper already prepared. If he asks me something about, I will prepare. So when I arrived to the airport to pick him, he said to me, I have a question, and the question 1, who was Santaló? And I say, I have no idea, I'm sorry. So I was prepared for everything but except for the name of the talk. But I had a joker in my pocket, and when we arrived to the hotel, Tomás, who was the person I named before, I was sure that he was going to answer him. So at the end, Tomás explained him in detail who was Santaló, and we saved the situation. Last thing is that yesterday in the dinner, we asked him if he has any petition to see anyone in the university, and he asked us, I would like to see the students. So thank you very much for coming.
Thank you very much for the super nice introduction. It's a little embarrassing. So the two gentlemen who are standing, I think you can take the chairs and maybe put them down there, the three. That would be okay. Yeah, just take the two chairs down there. Okay, so the paper was just published in the wonderful math journal that you heard about, Learning Algebraic Varieties from Samples. This was a project with 3 young people, 2 postdocs, and 1 graduate student from Berkeley. And here's the idea. So many young people like you, many students ask us, the older professors, what about data science, right? Everybody talks about data science. And the question is, what area of math should I study to prepare myself for data science and interact with data science? And the answer is your area of math, right? Any area of math has the potential of interacting, whether it's differential equations or dynamical systems or algebra, algebraic geometry. You can think about data and make your mathematics relevant for the bigger picture. So what I'm trying to do in this talk is to make this case for algebraic geometry, the study of algebraic varieties. So let's jump in. Suppose I have R polynomials, f1 up to fr, in n variables, x1 up to xn, with real coefficients. We're going to be interested in the common zeros of those polynomials. So this will be a subset in R to the n, or if I allow complex coordinates in C to the n. And such a set V is called an algebraic variety. So an algebraic variety is the zero set of several polynomials and several variables. Now in applications, often these polynomials are homogeneous. All terms have the same degree. What this means, if you have a solution and you scale it, it still stays a solution. And it's quite natural in that case to replace the affine space by a projective space, so to work either in real projective space or complex projective space. And I learned that several of the students are actually taking projective geometry, so this will be familiar to you. So in this picture we see 3 varieties. The circle, the blue circle, is a variety. It's a zero set of the polynomial x squared plus y squared minus 1. The green ellipse is a variety, and the intersection, the 4 red points, is also an algebraic variety. Now our group at Max Planck is called the nonlinear algebra group, and nonlinear algebra in particular extends and generalizes linear algebra. So linear algebra is the study of linear spaces where the polynomials are linear polynomials, and that's something that's very familiar to all of you. But in nonlinear algebra, algebraic geometry, we're allowing nonlinear equations in unknowns. Now I should also say the word variety is not a scary word. Many applied people, engineers, are a little scared of this word. They like words like manifold, model, shape, or space. So your friends will talk about manifold learning. Manifold sounds nice and soothing and smooth, but the word variety is actually much more accurate. So one thing I like to tell you is that actually varieties are often the right concept because they allow for singularities. They have a nice algebraic description. So one message of this talk, the word variety is not scary, even if your friends like the word manifold better. Now, if we have a variety the first observation is different sets of polynomials can cut out the same variety. In fact, if you have a variety, it only depends on the ideal generated by the polynomial. So the ideal is all polynomial linear combinations. So if I have a bag of polynomials and Thomas has a bag of polynomials, and if each of my polynomials is a linear combination of his polynomials, and each of his polynomials is a linear combination of my polynomials, then we have the same variety. Now there are lots of algorithms for dealing with this, Gröbner bases in particular, and they will reveal geometric features about the variety. Now variety walks into the door, and here are the first 2 questions we should ask him or her. First question, what is your dimension? How many degrees of freedom do you have? Second question, what is your degree? How curvy are you? So for example, here we have one equation in 3 variables, x squared plus y squared plus z squared minus 2xyz minus 1. That cuts out a surface in 3-dimensional space. This is the picture of the surface. So this is a variety of dimension 2. It's a 2-dimensional variety. A surface has 2 degrees of freedom. Now this surface has degree 3. You can see this algebraically because the largest term here has degree 3. Or you can see this geometrically if you stab this surface with a line, with the linear space of complementary dimension. It will almost always meet the surface in 3 points, but you can be unlucky. 2 of these might be complex and 1 of them might be real. For undergraduate students, this is a very nice textbook, Ideals, Varieties, and Algorithms. So the gentleman who writes his master's thesis in partial differential equation, it's not too late. You can brush up and read this undergraduate textbook. Now, if you do like manifolds, and if you're worried about these singular points, now something happened. Maybe. Okay. So, no. Okay. So, now these corners are the singular points, and the singular locus is a proper subvariety. So if I have a variety V, then the bad points, the singular points, are exactly those where the Jacobian matrix drops rank. So they're defined by appropriate minors, subdeterminants of the Jacobian. And well, if you remove the singular locus, then what you have is a manifold, and everything you know about manifolds and data on manifolds apply. You just have to be a little bit careful at the singular points. But in fact, very often in applications, the singular points is where all the action is. So we have to keep track of the singular points. Now, if you're a student, you're completing the class of projective geometry, you're not sure whether you should take algebraic geometry, for instance, with Professor Arondo. What do algebraic geometers actually do? So the simple, best answer I can give is they study the 27 lines on the cubic surface. So to really understand what makes algebraic geometers go, it's really nice to know that every smooth cubic surface over the complex numbers contains 27 straight lines. That's a very, very good point of entry. So that's my brief introduction to algebraic geometry. Every cubic surface contains 27 white straight lines on the blue cubic surface. Let's get to data. So I'm going to be given m points in n space. So I have data points u1, u2, up to um. I'm going to call this set of data points omega. And these have real coordinates, and they are either a point in real n space or in projective n-1 space. So I might know for some reason that's part of my data that these are actually, the problem is scale invariant, and I think about this as a projective geometry problem. Now these are sampled from an unknown variety V, and the goal is we'd like to know what is the variety. That's the task. Okay, so there's some unknown variety, and all we get to see is m samples on that variety. Now we have some variety. The first question you should ask, a variety walks into the door. First question you will ask him or her is, what is your dimension? How many degrees of freedom do you have? So, for example, let's say n is 2 and m is 27. We might be given these 27 data points in the plane. Now, what is that unknown variety? What is the dimension? Well, of course, the points themselves is just zero-dimensional, right? They're just a bunch of points. But all of you look at this, you really see some continuous object, and you think about the circle, right? So I think we can all agree that the answer is really there is some true variety, maybe given by this ideal, generated by this blue equation. So this is the kind of thing we'd like to do today. So I'm given a sample of points, and I'd like to conclude what is the algebraic variety. Okay. Now, what about the data? Now, of course, it's clear in applications we will never have exact data. So in any real-world scenario, if you work with medical doctors or any kind of scenario, your data will not be exact. There will be numerical data, there will be noise in the data, there will be outliers in the data. And that's very, very important. And statistics has important methods for dealing with this. So in the talk today, in the article, I'm going to assume that the data are exact and perfect. Right? So just for the purpose of the discussion here, I will assume that I have m data points that are exactly sampled from an unknown variety V, with the understanding that in practice, noise and outliers are very important and need to be dealt with. Now, another remark is, how do we sample? Right? Now, for example, suppose the variety has a rational parameterization. Suppose we have a map into our dimensional space whose coordinates are polynomials or rational functions in some parameters. Well, then it's easy to make samples. You just plug in parameter values. You just plug in parameter values, you get a point. You plug in other parameter values, you get another point, right? So if you have a nice parameterization by rational functions, then it's very easy to make points. But algebraic geometers know that most varieties do not admit such a parameterization. For example, if you have a smooth plane curve of degree 3 or more, no such parameterization exists. So let me give you a concrete example. Let's take this polynomial in two variables, x and y, of degree 4. This is something called the trot curve. The real curve consists of these four ovals here. So the red picture is the real curve. And this curve does not admit a rational parameterization. It's a smooth plane curve of degree 4. Now this is kind of a famous example. This curve has 28 bitangent lines. So a bitangent line is a line in the plane that touches the curve at 2 points. You can see there are 4 connecting any two of the ovals, and then any oval is a bean shape, so there's another 4, so there are 28 real bitangent lines touching the curve at, at 2 points. Now 28 is almost 27. It's the same. This is the same picture as the 27 white lines on the cubic blue surface, right? Because if you sit on the blue surface, suppose you sit on the blue surface with your camera and you take a picture of the blue surface and the white lines. Well, the picture will live in the plane. This picture, this projection will double cover the plane. Each camera ray will pierce the surface twice. It will cover the plane, and it will ramify exactly at a quartic curve. Each white line becomes a bitangent, except there's one more bitangent. That's the camera, right? The camera cannot take a picture of itself. It gets blown up, it becomes a line. So this is what algebraic geometers do. They study the 27 lines of the cubic surface, or the 28 bitangents of the plane quartic. They've done so for hundreds of years. And I also learned that there's some students of Galois theory in this course. And in Galois theory, we learn how to understand the symmetries of these figures, right? So there's a very, very nice symmetry group on these figures for the lines. The symmetry group is called E6. For these in free space, for this is called E7. So please talk to your teacher in Galois theory and ask them, how to figure out the symmetries of these pictures. Now back to data science. Now in algebraic geometry, most varieties are not rational or unirational. They do not have a rational parameterization. But the opposite is true in applications. When you encounter an algebraic variety in an applied setting, quite frequently, it will have a rational parameterization. And the reason is that the variety and the parameterization model some generative process. So if in the physical sciences or in statistics you have some model, or in biology, very often that model describes a process for generation of data. And the process itself often is given by polynomials or rational functions. So if you have a model that describes a process, very often the variety will be rational. Okay? That's important to keep in mind, because after all, we're trying to learn an unknown variety, right? So if you're a pure algebraic geometer, then you might guess this unknown random algebraic variety would not be unirational, but from an applied point of view, it often is. There will be 3 running examples in the talk. There's the trot curve that you've seen. The second part is the group of rotations, SO3. So SO3 are 3x3 rotation matrices. So this lives in the 9-dimensional real space of 3x3 matrices. It's a group, it's a manifold, but it's also a variety. Right? So it's a variety, it has a nice rational parametrization, and we can write down the ideal. It's described by 10 polynomials and the 9 unknowns. So there's the matrix equation, X transpose X is the 3 by 3 identity matrix. So X is a 3 by 3 matrix of unknowns. So this is a system of 9 quadratic equations and 9 unknowns. Then we throw in the requirement that the determinant is equal to 1. That's a cubic equation. And so this describes our ideal. Now, rotations arise in many, many applications, computer vision, structural biology, and so on. And I think I should at least quiz at least once the people in the last row. So maybe the gentleman here, what is the dimension of the group of rotations? How many degrees of freedom do you have in picking a 3 by 3 rotation matrix? You can ask the experts next to you. Is it clear? So I have I'm talking about rotations in 3-dimensional space. How many degrees of freedom do I have to make a rotation matrix? 3? Okay, absolutely perfect. Okay, so the answer is 3. So the dimension is 3, the degree is 8. Okay, so the curviness is 8. So this is a 3-dimensional manifold of degree 8. Now the third example is low rank matrices. So n matrices of rank 1, that's a very important variety. That's also rational, it has this parametrization, right? So matrix has rank 1 if it's the product of a column vector and a row vector, right? That's a rank 1 matrix. Nowadays, in the day and age of data science, matrices are much too small to fit all the data, so that's why we use tensors, right? It's not called matrix flow after all, it's called tensor flow, and a tensor has rank 1 if it looks like that, right? Very good. So to algebraic geometers, this is known as the Segre variety. To statisticians, it's known as the independence model. Same question. First question is, what is your dimension? Second question is, what is your degree? In this case, they're simple formulas in terms of m and n. But let's get back to our problem. We have a sample of m equals 40 points in a space of dimension n equals 6. They're perfect data, they're integers, they're exact data, and they're exactly sampled from the variety. Now what's the variety now? Now earlier you saw the 27 points on the circle and all of you said that's the circle. But now we have still a very tiny low-dimensional data set. This is not big data. This is 40 points in 6-dimensional space, a very small variety. Now, what is the variety? That's the question we'd like to answer. Well, let me tell you what it is. So here's what we did. This is how I made the data. So I picked a random 2 by 3 matrix of rank 1. And I scrambled up the entries. I called them x1, x2, x3, x4, x5, x6, and I plotted. Right? So my data set, all of the points satisfy some very simple quadratic equations, namely the 2 by 2 minor. So for each of these, x1 times x6 is equal to x2 times x4. Right? So if you look at this for a little while, then you can figure out that there are these 3 nice quadratic equations, and you will learn that will fit like this into a 2 by 3 matrix. Okay, so again, for a geometer, we're in projective space. We have the Segre threefold, and for a statistician, for example, this is called the independence model for 2 discrete random variables, a binary and a ternary random variable. Okay, this is our task: input, output. Okay. Let's talk a little bit more about estimating dimension. So when we embarked on this project, we said, well, let's first look at the literature. Always a good thing, right? Whether you're an experienced scholar or master student, you should always look at the literature first. Now for students, there used to be this thing called the library. Okay? The library was a physical place that contained things called books. Okay? It is a very, very good idea to go there, okay? It's great to go to the library. Of course, online search is also good, and the Wikipedia, after all, is the source of all wisdom. but there is this thing called the library that contains very nice old math books. Now, we checked the existing literature, mostly from computer science, on intrinsic dimension of a point sample. And we found that there's a lot of literature, and we were trying to make sense of this for our data. Okay? So the key point in our study is that the sample size, m, is fixed. Okay? So I have my data from a medical doctor, and this is the data set. Right? I cannot get more data. It would be too expensive or unethical to get more data. M, that's it. I have m points in n space. I cannot sample more. Okay? Now, there are various estimators in the literature. What they do is they calculate a number, and that number depends on the data, on the sample, and a scale parameter epsilon. Okay? So epsilon is a parameter that I use to tell me at what scale do I want to look at the data. Okay? So if I look at my data at scale epsilon, there will be a dimension. Dimension is a positive real number. Okay? Now, of course, in algebraic geometry or topology or differential geometry, typically what you learn is that the dimension is a non-negative integer. Okay? But here in this context, it's quite natural to average and look at positive real numbers. Again, epsilon does not tend to 0. This would be meaningless, right? Because if I look at my data set, this data set at a very, very small scale epsilon, I will no longer see that this is a circle. I just see discrete points. Okay? That's very important. Now, the gold standard is linear algebra. So in your linear algebra class, you hopefully learned about the singular value decomposition of a rectangular matrix. And in the statistics class, that's called PCA, Principal Component Analysis. And here's what we do. I take my data, omega, and I write it as a matrix. So I take my data, I write it as a rectangular m by n matrix, and the singular value decomposition finds an orthogonal matrix T1 on the left and another orthogonal matrix T2 on the right that produces a rectangular matrix with diagonal entries. A diagonal matrix whose entries are non-negative real numbers. They're called the singular values. Now, in principal component analysis, we're asking the question, is my data set on a linear space? And if so, what is that linear space? And what you do is you look at the singular values and you take the index k for which the jump on a logarithmic scale between the two adjacent singular values is the largest, right? So a matrix has rank 1 if the singular values sort of are 0 or close to 0 after the k, right? In your numerical analysis class, definition of rank. So that's what you do. Right? You take the data, so you ask the question, are my data on a linear space, and what's the dimension? You do the PCA, and you look for that number k. That's the dimension of your linear space. Now, the first nonlinear method that we found in the literature is called nonlinear PCA dimension. Here's what you do. You take the data, you use your parameter epsilon to cluster the data. Right? So you have my data set. I'm going to say two guys are in the same cluster if they're epsilon apart, right? And then you take group clusters together by using epsilon. Then on each cluster, you calculate the PCA dimension, and you take the average value. We're going to call that the NPCA. Okay, that's one notion of dimension, and that's going to be a rational number. Now, here's other things you can do. Very often, in many, many contexts, you look at omega as a finite metric space. So you really don't care so much about the points themselves, but all you care about is the pairwise distances among the points. So if we're in n space, maybe we can take the Euclidean metric. If I'm told that my points are in projective space, I can take a so-called Fubini-Studi distance. It's basically an angular distance on the sphere using trig functions. And then let me write C epsilon for the fraction of pairs that are close, that are epsilon close. Right? So there are M choose 2 pairs. And I look at, among those M choose 2 pairs, I count how many are closer than epsilon. And then the ratio of that number divided by M choose 2, I'm going to call C epsilon. Then the correlation dimension is the logarithm of that number divided by the absolute value of the logarithm of epsilon. Again, that's a real number, and that's an estimate for the dimension at scale epsilon. There's something called box counting dimension, having to do with the fraction of boxes occupied by the samples. And there are many more estimators of dimension in the literature. Now, all of these estimators, there's theorems, and these theorems say these estimators are consistent. They're consistent in the sense that if you take more and more data, you sample very finely from a manifold, you will, in the limit, get the correct dimension. That's nice, but it doesn't help us so much because m is fixed and epsilon doesn't change. So there are these theorems, they're theoretical theorems, but being an algebraic geometer, I'm a practitioner, right? I have a fixed m, and m doesn't go to infinity. Here's another one. So there's also something called persistent homology dimension. I'll get to that. There are two more statistical ones. So the first thing that we did, we implemented all of them, and we compared them. And so we're defining the dimension diagram of a sample to be the graph of the map, right? So I scale my data so that the relevant epsilon is between 0 and 1. I simply look at the graph of the function that takes epsilon to the corresponding dimension at scale epsilon, and I plot the curve. So then these are the typical curves I get. So here epsilon is between 0 and 1. Here I have the possible dimensions, 2, 4, 6, 8, 10. And at different scales, these are the different methods, I get different values. So here it goes. In pure math, the dimension of an object is a positive number, like 7. Okay? But here, the dimension is a diagram like this. Okay? So we're proposing that we simply have a dimension diagram. And so here is something. Suppose here we took 600 3x4 matrices of rank 2. Maybe I know that my data are scale invariant, so this is a 9-dimensional variety in projective space of dimension 11. Degree is 6. It's cut out by 4 cubics, the 3x3 determinants. And this is the dimension diagram that our software produces. And 9 is sort of not bad. See, if epsilon is too small, you just get garbage, but there's some reasonable range of epsilon where they roughly agree. And this sort of centers around 8 or 9. So we have some vague idea that this sample comes from some variety of dimension 8 or 9. Okay, that's the best we can do because m is small. M is 600. The other ones, yeah. So maybe there's a fantastic paper in an amazing journal that has all the details, okay? So there are other notions. There's something called Baker-Levina dimension. These last two are very statistical. So they're coming from the statistics literature. So we implemented, there's roughly 10 to 15 in the literature. We picked those 6 to implement, and then we compute these diagrams, okay? So now what have we accomplished? At this point, we have our sample. We have a rough idea what the dimension, of the variety could be. The next thing, we're going to ask connectivity questions. We're going to apply topological data analysis to our sample. So this is a very popular subject. So algebraic topologists have connected a lot to data science. And there's a whole field called topological data analysis. And I like to make some points here that this should interface very well with algebraic geometry. And one reason is that the topology of real and complex varieties has been very well studied. So data sampled from algebraic varieties provide a very good test case for topological methods. Okay? So if you have friends in the local computer science department who like applied topology, this is a good source of data. Now coming back to the trot curve, the trot curve is a plane curve of degree 4, the genus 3 curve. This is the real picture. This is the complex picture, the complex solution. So a complex curve is a Riemann surface. One complex dimension is 2 real dimensions. So the complex picture looks like this. It will be a Riemann surface, the same equation, the same curve, but it looks like this. These are the complex points. Genus 3, the number of real components is at most 1 more than genus. This is a tropical curve. So in tropical geometry, we also have the 3 cycles. This is the same curve, right? But in algebraic geometry, we learned that the same curve can be drawn in different pictures. We can have a complex picture, a real picture, a tropical picture. And each of these pictures provides a very good testing ground for your friends in computational topology. So persistent homology, what it does, it also has a scale parameter epsilon. It computes the homology groups depending on the scale parameter. So we're applying this here to this sample on the trot curve. So I pick, this is the 0th homology, so we're counting connected components. This is the first homology, so we're counting loops, and so on. So we see, and the way we do this is we pick at scale epsilon little balls around the sample, and then we connect two samples by an edge if the balls intersect, and then we form the simplicial complex, the stingiest simplicial complex made of these edges, and we compute homology. This is standard, it's called persistent homology. Now what you see is that here as epsilon, so as epsilon is in the small range, there are 4 connected components. That's consistent here. But then as epsilon goes larger, the balls get larger, you see 1 circular connected component. Now the first homology detects cycles in the data. So first homology on this data set, it detects the intrinsic geometry of the curve, right? So at small epsilon, I'm seeing 4 cycles. That's the intrinsic geometry of the sample. But at larger scale, it detects the extrinsic geometry of the cycle, which is a single cycle, right? So there's an intrinsic feature. You see 4 cycles, but extrinsically, they're grouped to form a big cycle, and that's what's picked up by persistent homology. Now, how is this related to the true homology? Well, there's a celebrated work of Nyoga, Smale, and Weinberger. They give conditions under which a sample from a compact manifold will reveal the true homology. And a key ingredient is a concept from computational geometry called the reach. Let me define this for you. So suppose my variety is this black curve. Then every point in the plane has a closest point on the curve. Right, so there's some curve here, maybe this curve, our curve, and each of you is closest to some point on the curve. Except some of you maybe cannot make up your mind. They're the undecided points, and that's the medial axis. So the medial axis is the set of all red points who cannot make up their mind, the set of all points whose distance to the variety is attained twice. Right? In this case, the medial axis is this tree-shaped thing in the middle. So this red point has 2 closest points to 2 blue points. The medial axis is a semi-algebraic set. Real algebraic geometry, of course, being a very, very important subject to study. But these things are hard to compute. And the reach, by definition, is the shortest distance from the variety to its medial axis. That's attained down here in this example. Now the punchline, so these concepts are very important when you try to quantify how accurate persistent homology captures the true connectivity, the true homology of the variety. Well, this medial axis, Zariski closure anyway, is a variety, and the reach is an algebraic number. And there are 2 recent papers that discuss this. And one consequence is the following. Let me just illustrate this. Again, this is our data set, the trot curve. Here is the persistent homology in dimension 0 and dimension 1. I claim that the bars, the locations where the bars begin and end, they are exact algebraic numbers. Right? Because, for example, here, this blue bar, epsilon is 1/8. Then here, where this one ends, that looks like 0.2, but it's actually this number. It's this exact algebraic number. Okay? So that is the distance, by the way, between 2 of these ovals in the curve. Okay? So that's the second sense in which algebraic geometry can inform applied topology. It can provide exact representations for the bars that are computed in applied topology if we're sampling from an algebraic curve, say. Here's a third one. Maybe I'll skip this. You know, I had this very, very, very nice introduction that went on for 15 minutes, so it means I have to skip a couple of slides. Let's skip this, and let's move on to the next topic. Finite equations. What have we done? We have a sample. We have some rough idea of the dimension from the dimension diagram. We have some rough idea about the connectivity and the holes in the data from persistent homology. Now let's actually try to find equations. We need to do some interpolation now. Let me write M for the set of monomials, for a finite set of monomials and n unknowns, and Sm for the space with that basis. Now if I have my data set omega, I'm going to write U sub m omega for the corresponding Vandermonde matrix. That's a matrix that has m rows, one for each data point. There's a column for each monomial. In any entry, it's the value of the monomial in that column evaluate at the point in the row. Okay? That's called the Vandermonde matrix. So for example, if we have 3 data points on the line and n is 1, then this matrix looks like this. Okay? So we take the monomials in the first data point, second data point, and third data point. Now the observation is that we need to calculate the kernel of this matrix. Right? So the kernel of this matrix, well, these are linear combinations of m that vanish on the right. Right? So this is the intersection of I omega, the ideal of the known point cloud. So I omega is the ideal of all polynomials that vanish on the finite set omega. Okay? But I'm intersecting this with this finite dimensional subspace, and that's this. This intersection is the kernel of the matrix. Now I omega is a superset of IV. IV is the ideal of the unknown variety. Right? So I have the IV, that's the ideal, the unknown ideal of the unknown variety. It is contained in I omega, which is the ideal of the point set. Okay. So what are we going to do? Of course, we're going to use numerical linear algebra, and there are 2 conflicting goals in choosing my monomials. Right. So what are those? Well, here are 2 things we'd like to happen. I would like to choose m large enough so that the ideal of the unknown variety is actually generated by the subspace. It's generated by polynomials supported on m. Okay? On the other hand, what I also want, I want the inclusion of this finite dimensional vector space, IV intersected Sm, inside I omega Sm to be an equality. Right? Now, if m is too big, this will, not be an equality because there are many, many, many polynomials that vanish on the finite points but not on the variety. Right? So if I had these 27 points on a circle, I can certainly find lots of polynomials that vanish on those 27 points but not on the circle. I don't want those. Right? So I'm in the middle. Right? So I have to be in the middle. I have to compromise. Right? So if m is too small, then A will fail. If m is too large, then B will fail. That's what we're up against. Now in our code, we implemented 3 methods for calculating the kernel. So we coded everything in Julia. So numerical methods, you probably know about MATLAB. A lot of people nowadays like to do their numerical linear algebra in Julia, open source software. So in Julia, we have 3 methods. The singular value decomposition is accurate and fast, but it has a big disadvantage that if you get the kernel, it's very hard for humans to read it. Right? These are orthogonal bases for the kernel. But as an orthogonal basis, it's very dense. It's very, very uninformative. Right? You get polynomials that you cannot interpret. Okay? You can do the QR factorization or row-reduced echelon forms. Not as fast, but it gives you a sparse basis and has the advantage that humans can interpret the answer. 4th topic. Back to algebraic geometry. What have we done? Folks in the last row. Your collaborator from the medical school has a data set. First thing is we get some rough idea what the dimension of the variety is. Second thing, we get some rough idea about connectivity and topological properties. Third, we find some equations that some polynomials that vanish on the sample that we believe define the variety. Well, we're not sure, right? So now we're going to apply some algebraic geometry to test how good we are. So now we have a set P of polynomials that vanish on our data set, and we're hoping that it cuts out the true variety. But we're not sure. Right? Now we can use symbolic methods, the kind that Professor Recio likes, or numerical methods that some young people like, to answer the following 3 questions. 1, what is the dimension of the variety? 2, what is the degree? and maybe find irreducible components. We're going to apply that to the known polynomials, right? Because we have some polynomials and we're hoping that they... Let's see an example, okay? So somebody gives us a sample of 500 points in 6-dimensional space, and they tell us that it's drawn from some generative model. So it's a generative model that describes some process in biochemistry, okay? Well, let's find some polynomials, right? So there are no, this is not a linear space, there are no equations in degree 1, 2, 3, no equations, but there are 2 equations in degree 4. So we're picking a sparse basis, and we find these 2 polynomials in A, B, C, D, E, and F that vanish on the sample. Maybe they cut out the variety. Or do they? Well, they don't, right? Because it turns out that the ideal generated by P is not a radical ideal. Meaning this does not generate all the polynomials that vanish on some set. There are more polynomials, right? So we go up, we increase the size, we look at the Vandermonde matrix at level 5, and we find 2 new quintic equations. Now we apply, sorry Thomas, we're applying numerical primary decomposition. We're decomposing this variety, and we learn that there are actually 2 irreducible components, right? So it is radical, but it's not prime, but there are 2 components. So to distinguish the 2 components, we have to increase. We have to do one more step in our Julia code. So we look at U6. That's good enough. We're finding new 4 sextics, and that's actually a prime ideal. Right? So now we're fairly confident, right? Because this prime ideal, see, for the differential equation people, so prime ideal is like prime time or prime rib. Okay, it's like, it means it's a very good ideal. Okay, so a prime ideal is a good ideal. So this is now a prime ideal, so this means we have a chance that these are the equations. And now we have to analyze, of course, the data, so this takes a little while. So after looking carefully at these equations, you unravel the mystery. So V in this case is the variety of 4x4 Hankel matrices of rank 2, where the antidiagonal entry has been deleted, projected out, right? So I sample these S's and T's, I multiply, I get a 4x, so Hankel matrix means I'm constant along antidiagonals, and then I delete this gives me A, B, C, D, F, and I ignore the X entry here. That's how I made the data, okay? So this is a step, right? Once you're here, then, you know, you need to analyze, and you can learn that this has this determinantal structure. So in applications, very often, they're nice determinants. Now, some of you might think, I don't know, this guy is computing, you know, in Julia, numerical things, it's all inaccurate. I want to do pure math, because pure math is beautiful. Let's talk about beauty for a moment. Okay? Now, certainly algebraic varieties are very beautiful, right? I mean, here is the spectrahedron we saw. Here is the Como surface, very beautiful, you know, quartic with 16 singular points. It's a abelian surface, mod involution, the 16 two-torsion points and Jacobian. I mean, nothing could be more beautiful than that, right? The only thing that's more beautiful than the picture of the variety are the equations. The equations are more beautiful even, right? I mean, it's algebraic geometry. Geometry is really beautiful. Algebra is even more beautiful. Let's look at these equations. I mean, they're so beautiful, right? So here we have the Pfaffian of a skew-symmetric 6x6 matrix, right? So if you have a skew-symmetric 6x6 matrix, the determinant is the square of a cubic polynomial. A very beautiful polynomial having 15 terms, one for each matching in the complete graph of size 6, right? So 6 people go to a party, they have 3 cars. There are 15 different ways, you know, of splitting up, you know, 2 groups, and each of them has a sign. Quite beautiful, that's the Pfaffian. The determinant of a 2x2x2 matrix, right? So the 2x2x2 hyperdeterminant, you have a 3-qubit system. Very beautiful, right? The hyperdeterminant of a 2x2x2 tensor. Here we have the Schoenberg matrix. If you have a finite metric space on P points, let's say you have P biological taxa, organism, you know the pairwise distance, right? Then you can form this P minus 1 times P minus 1 skew-symmetric matrix with these entries. So Dij is the square of the distance. That's the Schoenberg matrix. Very, very beautiful. It has the property, it tells you whether your metric space is Euclidean, right? So those p points came from p points in some Euclidean space if and only if this beautiful symmetric matrix is positive semi-definite. And if it's positive semi-definite, it has some rank, and the rank of this matrix is the embedding dimension, right? Your data came from 3 space if this is a rank 3 matrix, okay? So what I'm trying to say is that when you learn these varieties, it's good to know a repertoire of varieties. If you learn topology and you want to apply, so if you're in some area of math and you want to apply it to data, right? You better have a very, very good idea of the repertoire in your area of math. If you're in low-dimensional manifolds, you better know some really good, beautiful manifolds. And here with the varieties, as I said, it's good to know picture, even better to know equations. Let me wrap up. So I think some of you maybe go to another class at 2. So let me wrap up. So all algorithms that I discussed are implemented in a Julia package called Learning Algebraic Varieties. You can try it out. In the last section of the paper, we have a case study with some real data set. So let me go over this. So there was a data set that's been analyzed, discussed a lot in the literature. So n is 24 and m is 6040. That data set are samples from a configuration of 8 points in 3 space, right? So if you have 8 points in 3 space, you can think about this as a vector of length 24. And they represent conformations of a chemical molecule of cyclooctane C8H16. Okay, so this is a ring of 8 carbon atoms, and at each carbon atom you have 2 hydrogens attached. Right? Now you learn in high school chemistry, right, there's a dihedral angle, right, the 109-degree angle, remember that from high school chemistry, right, there's an angle of 109, that's what they do, right? If I'm carbon and the 4 of you are hydrogen, we'll make angles of 109 degrees. So what are the constraints? Well, along this atom, right, so along this molecule, the pairwise distance will be, let's normalize it to be 1 if we're 1 apart, right? So any 2 carbon atoms, let's say, have distance 1. But then, because of the dihedral angle, also the guys that are 2 apart have a fixed distance. In fact, that's 8/3. The square root of 8/3 is the distance between the ith and the ith plus second. Well, I already told you about the Cayley-Menger matrix, right? So if we have 8 points in 3 space, there's a 7×7 Cayley-Menger matrix, and the variety is the determinantal variety that's supposed to have rank 3. We discussed this. So we analyze this. So there's a lot of literature, especially applied topologists have looked at this. So the solution set, the conformation space is a nice topological space. It's singular. It's a union of a sphere and the Klein bottle glued along 2 circles. We confirm this. So there's standard persistent homology. There's our variant that's enhanced by algebraic geometry. Let me not get in this, but our software confirms this. And in fact, finding equations, finding equations helps a lot in getting more accurate understanding of the homology. So we analyze this. Time is up. So data science is about finding, understanding needles in a haystack. You have a very, 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 very high dimensional space of conceivable data. You have a very, very tiny thing of actual data that you can actually see. That tiny thing has many names. Manifold, model, variety, and it's the geometry of this data that's very, very important. So the institute I'm in, the Max Planck Institute in Leipzig, so some of the young people started a math of data initiative, and you can visit, if not in person, then online. So this is something we do in Leipzig, but I'm sure that people here are interested in similar topics, and I'd love to talk to you. Thanks for your attention.
¿Tenéis preguntas? ¿Me oís? ¿Ahora se oye? A ver, ¿tenéis preguntas? ¿Alguna pregunta tenéis? Si tenga preguntas, sería capaz de formularlas en inglés.
There's a question here.
usually when you encounter applications of this varieties, they're usually irrational. Can you give us an example before how you face an non-irrational variety?
Yes. So there are some situations. So sometimes in statistics, so typical models like, in phylogenetics or hidden Markov models, they're all rational. But as soon as you restrict, so sometimes some of the random variables, they take particular states. So then it's quite natural that you slice the variety, maybe by a hyperplane. So typically, even if you have a nice rational, unirational variety, as soon as you slice it with the hyperplane, it no longer has this property. So there are some natural situations where you just fix some value to be a particular number, and then that's the case. So
more questions? Now I have the microphone.
I have two questions. The first one is, you mentioned library books. How many books have you written or co-authored?
Many, many.
Now, the second question is about a Cayley-Menger determinant. Is it related to a volume in this case, or
Yes.
is it a generalization?
Yes. So this is a nice exercise, right? So here's an exercise for the students, okay? Suppose you have a tetrahedron in three-dimensional space, okay? And all you're given is the 6 edge lengths of your tetrahedron. And we'll write down the volume in terms of the 6 edge lengths. Okay? Is that clear? The question clear? You have a tetrahedron, and you're only told the 6 pairwise distances. Well, answer is you form this 3x3 matrix. So you do this. Here you do. So now P is 4. This is a 3x3 matrix. And Dij is the square of the distance. You take your distance, you square it, you fill it into this 3x3 matrix, you calculate the determinant, you take the square root, you divide by 8, that's the volume. Okay? Exercise.
More questions?
Have you done any work on analyzing the sensitivity of these procedures to the noise in data?
Okay, the answer. So the question was, did you do any work on noisy data? We have not done any work on noisy data. So this was just submitted and published. It was submitted in April or May and just published. There is some work. So certainly in the linear, let me say a few words about this because this is a very, very important next step. So the gold standard, I said, is PCA. And of course, in this case, there's a lot of work. So finding, whether data on a linear space, there's a lot of work in statistics on noisy data. There's also some very nice work by Ma from Illinois, where the variety is a union of linear spaces. So you suppose you have a variety, but every component is linear. So maybe you're in 3 space. You have some lines, some planes, and you sample from such an arrangement. And there are some very careful analysis. In this case, we haven't done it yet in the general case. But this is a very, very important problem. But you really need somebody who's trained in statistics to do this.
Other questions? Well, I have 2 questions. Is there any limitation for the distribution of the sampling points? For instance, the points are in a quite a strategic way that you see the circle?
Very, very good question. So again, another thing we did not address in this paper is how we sampled. It's a very important question. How do you sample? But this is an active study. So there's a work right now. So Paul Breiding, he's a brilliant young guy. He's sort of more of a numerical analyst. So he's just finishing a paper on uniform sampling on real algebraic varieties. And that's a very, very important task. So he has a paper where he says, I take a compact real algebraic variety, and I can actually sample from the uniform distribution, provably. But it's quite difficult, because you really need to sort of combine real algebraic geometry with integral geometry. Work of Santaló comes in, unsurprisingly. And so this is the next paper by this guy, is on uniform sampling. If you're in a situation, for example, if as a group structure, as a homogeneous space, as a Haar measure. So then you would like to use sample from Haar measure. So I would say it's beginning, but in this paper we did not really analyze the sampling schemes.
Okay. And another question is, many times for computing dimension, one uses the tangent space. So is there any estimation about the tangent space
Well,
from the sample
Well,
points?
that's very funny because I'm skipping one slide. That's the slide, okay? So what we did is we said, let's improve persistent homology. Rather than picking little balls around the sphere, around the data, we're surrounding each data point by a little ellipsoid. So rather than taking spheres, we're using ellipsoids. Now, which ellipsoid should we take? Well, that's driven by the tangent space. So what we do is we estimate this tangent space at each sample point, but we're using the equations we found. Remember, at some point we have some equations that vanish, and we use those to get an estimate of the tangent space, and then using that estimates we can build a better persistent homology code. So absolutely, the tangent space is important, assuming that your point is at a smooth point of your variety.
And finally, I make a simile before with cars. So you speak about software. So how fast is your software? Imagine you have a sample of 5,000 points. How much time it needs to?
I mean, it's a numerical software, so speed is generally relatively fast, but well, the output is meaningful. That's a different question, right? I mean, it really depends on the conditioning of the input. It depends on the degree of the equations you expect. So if it's quadratics and cubics, you'll find them quite fast. But this is already quite hard. So finding degree 6 equations is already more complicated. So, but I would say, up to 5,000 points in dimension 7, 8, it would be okay. Couple minutes.
More questions? So let's thank again the lecturer.